Hey everyone, welcome back to the physics past paper videos. Today we're going to talk about paper 2 from the May-June 2025 session, and the variant that we're going to talk about is 2.1. Before we jump into the paper, some resources that we have created for entire A levels. We have already packaged this in this grade booster pack, but what it contains is very exciting. So for AS, we have definitions and formulae. They contain every key detail, every minor fact. It's not notes and everything, but still it contains a revision. This table that you just saw is the reasonable estimates one. This contains all the definitions and formulae. This contains important derivations, the ones that come in the exam and the ones that are required by the syllabus. Like Likewise, we have frequently examined questions, which at the moment mostly focus on paper 2, but we are working in the next session to include paper 1 questions also. Then we have A2 definitions and formula, which is very similar to the AS1, key points and their details, their formulae. Not to forget their derivations. We know we often get the gravitational field derivations. This one, we often get that. We already are familiar with this, but this is still included in this, and the rest of all the derivations, important ones. Then we have the most important one, the paper 4 frequently examined questions. As you can see, we have structured it in a way that we have syllabus. We have syllabus on the left side, question and answer on following, and the years listed on the right side. If you don't see any year listed over here, that doesn't mean that it's not an examined question. It just means that it's an important question, but not very frequently asked. But anyways, there will still be questions, just like, for example, this one, which are very frequently examined. So when you see us doing A2 videos, A2 past paper videos, you will see us going through this quite a lot. Then we have A2 physics graphs. As you know, we all struggle with field and potential graphs, so we have got you covered along with their formulae. So just to help with the understanding. Last but not the least, we have paper 5 checklist. This is according to the marking scheme and the syllabus, whatever is required. And there are some worked examples from the past paper questions also. This one is, for example, paper 5.1 from October, November 2024. So although you might realize that this is not possible to be written in the space given in the exam, but still this is here to show you what details you can include, what are important facts that you need to write, what are best methods of procedure, and how to structure the table, how to figure out how to deal with the gradients and y-intercept, and how to work with safety precautions. Now, going back to the paper. So let's see the paper. Okay, define acceleration. This is a very simple definition, but this is in the important definitions and formulae book also, and in the frequently examined questions also. So this is just simply rate of change of velocity. Okay, so in an experiment, two objects A and B are released from the side of a building as shown in figure 1.1. Object A is released from rest at a height of 14 meters above the horizontal ground. Object B is released with an initial vertical velocity u at a height of 3.6 meters above the ground. Both objects take the same time to reach the ground, and they do not collide with each other. Air resistance is negligible. Okay. Calculate the time taken for object A to reach the ground. Okay, so since this it is dropped, it is released from rest, the initial velocity is 0. We are not concerned with the final velocity before reaching the ground, so we can just simply use 2 sorry, no, no, s is equal to ut plus half a t squared. S is given to us as 14 meters. This is 0 because u is 0. Half times by 9.81 times by t squared. We need to simplify this. So 28. So just to show you the calculation that we're doing, t squared is 2 times by 14 divided by 9.81. So t would be the square root of this. 2 times by 14 is 28 divided by 9.81. This is 1.689. So in two significant figures, we can write it as 1.7. Use your answer in B1 to calculate U. Okay, so in this, they have already told us that B also spends the same amount of time. However, the thing to notice over here, object B is undergoing two directions of motion. First, it is going upward, then it is going downwards. However, the net displacement this object is having is minus 3.6, considering if you take upwards as positive. For A, we just considered downwards as positive, but that was not a problem. But since this object is going two directional motion, bidirectional motion, so we will have to take a positive direction. So let's say original U was upwards, so final net displacement would be minus 3.6, and they are undergoing the same time. So how do we figure this out? So S is equal to ut plus half a t squared. Remember, we don't know what the final velocity is, so we can't include the final velocity equations. S is minus 3.6. U times by t, 1.7. This time A would be minus 9.81 because we are taking upwards as positive. So minus half times by 9.81 times by 1.7 squared. So one by one, we need to take things on the other side. So minus 3.6 plus 9.81 divided by 2 times by 1.7 squared. And then finally, divide this all by 1.7 to get u, which is 6.22. So you can show the working over here also. So u will be minus 3.6 plus half times by 9.81 times by 1.7 squared divided by 1.7. So this is 6.22 this way. Now, if you had taken downwards as positive, same as A, then there would only be a difference in signs, nothing else. The value would stay the same. So you might get it as minus 6.22, otherwise it's going to be the same. Just a difference of sign, this would be plus, this would be plus also. That's it. Right, okay. In a second experiment, object B is released from the same height and given the same initial speed as in B, but at a release angle theta to the vertical. State and explain whether the time taken for the object B to reach the ground is less than, the same as, or greater than the time in B. Okay, to understand this now, the vertical velocity has changed. So vertical velocity has now become q cos theta. Now, how does the cost graph look like? Cost graph looks like this. We only need to consider up to like 180 degrees. We don't even need to consider the 90, but still, okay, that's fine. You can look at that. So this is 0 degrees, and this is your cosine theta value. Sorry, cosine theta graph. So what this actually means is that your vertical velocity over here, vertical component of u over here, would reduce as you increase the release angle. So this already shows us that if your theta is greater than 0, u cos theta, which is the vertical component, is going to be less than u itself. And if the vertical component is less, it's going to spend less time in the air. Why? Because we saw this in, my bad, sorry. S is equal to ut plus half at squared. So if S is same, A is same, what's going to change over here? Time will reduce. That's all. So we are going to write the same, almost same description, that since the vertical component of u, u cos theta, will have lesser magnitude than u, it will spend less time to reach the ground. Okay. You could also include that it is achieving the maximum height faster or a lower height, basically. Reach less time. Although this is fine, but you can also write as it uh, achieves its maximum height at a lower point. That means a lower height. That you could also say as its maximum height is lower. By considering energy, state and explain the effect of the change in the release angle on the speed at which B hits the ground. Now, there is something that we need to understand over here. For example, if we are throwing this ball at the same level. So for example, this is the ball that is thrown at some angle theta, and it returns to the same level over here. We know that it's going to have the same v, same magnitude of v as it returns to the same height, because s has become 0, the displacement, net displacement has become 0. Another thing you notice over here, that the maximum height achieved, or the maximum change in gravitational potential energy, is going to be equal to the change in kinetic energy. But how will that affect? Will it be just simply half mv squared or something else? It will be related to the vertical component. So it will be half mv sine theta squared. It's related to that. However, the key point being the maximum height or the change in gravitational potential energy. So obviously this means that this is, you're talking about one half of the journey. Now, what if we are talking about something like this, where the change in gravitational potential energy is this, not this. We are not considering what is, because this is the net displacement. This is the net displacement. And whether we increase the release angle or not, the net displacement remains 3.6 meters. This is a fact that is given in the question paper. So the change in gravitational potential energy remains constant. So no matter what the speed, no matter what the release angle is, the net change in kinetic energy will also be the same. And this would be equal to this. So it does not matter how much we increase the release angle, it will be same as if it was just simply thrown vertically upwards. And somehow it travels 3.6 meters further from its initial position. So we can say that the net displacement remains the same. Therefore, net change in so net change in gravitational potential energy and consequently kinetic energy will be the same. Now the question was, state and explain the effect of the change in release angle on the speed at which B reaches the ground. So speed at which B reaches the ground is the same. That's it. Okay, all right, so moving on. State the principle of moments. Now, a common mistake students make is just stating that the anti-clockwise moment is equal to the clockwise moment, or the sum of moments, algebraic sum of moments is zero. However, that is an incomplete statement. The important part of that statement is that for a body in rotational equilibrium. So we are going to say for a body in rotational equilibrium, or for a body in equilibrium also, if you want to forego the rotation, although it would make more sense that since we're talking about rotational motion, for a body in rotational equilibrium, algebraic sum of moments is zero. Now, alternate statement from this is that sum of anti-clockwise moments is equal to clockwise moments. So this is an important part of that. Okay, so three objects A, B, and C are placed on a horizontal beam. Beam is in equilibrium, shown in figure 2.1. The beam is uniform. So uniform means uniform density, that means center of gravity is at the exact center and has a length 6 meters. Pivot is at the midpoint of the beam, that means that the center of gravity will have no moment about the pivot. Object A has mass 60 kg and is at one end of the beam. Object B has mass 45 kgs and is at a distance x from the pivot, and object C has mass 80 kgs and is at the other end of the beam. So the weight of A is 60 g, B is 45 g, and at the other end this is 80 g, like mg basically. Calculate x. Now the beam is in equilibrium, so according to this principle of moments, if the body is in rotational equilibrium, algebraic sum of moments is 0, or sum of clockwise moments is equal to anti-clockwise moments. Okay, so depending on which statement you want to look at, you can do it two different ways. Usually for anti-clockwise moments, we take moments as positive, for clockwise moments as negative, but only for the algebraic sum. You don't need it for sum of clockwise equal to anti-clockwise. But just to show you that what the algebraic sum over here means, the anti-clockwise moments are 45g and 60g. So 60g, so sum of moments counterclockwise or anti-clockwise plus or minus sum of moments clockwise is equal to 0. So 60g times by 3 meters plus 45g x minus 80g times by 3 is equal to 0. Now compare it with the statement sum of moments equals to sum of clockwise moments, sum of anti-clockwise moments. Clockwise moment is just 80g times by 3. Anti-clockwise are 60g times by 3 plus 45g times by 3. And as you can see, x, my bad. They're one and the same thing. If you rearrange this would become the same thing. Okay. Second thing, g is common in all of them. So if you divide entire equation by g gets cancelled out across the equation. 60 times by 3 is 180 plus 45x, 240 equal to 0. So 45x is equal to 240 minus 180. So this is going to be 60. 45x. So x would be 60 divided by 45. So 15, 3 is 45, 15, 4 is 60. So it's 4 over 3, which is 3.1. Sorry, no. 1 over 3, my bad. So 1.3 basically. So 1.3. So 1.3 to two significant figures. The beam is 0.8 meters above the horizontal ground. Object A is removed and is replaced by a spring connected to the ground and the beam showed as shown in figure 2.2. After the change, the beam is again horizontal and in equilibrium. So same condition applies. The positions of B and C are unchanged. Spring has an unstretched length of 0.59 meters and obeys the Hooke's law. Calculate the spring constant of the spring. Okay, so if everything else is the same, the positions of B and C and their respective masses, everything else is the same. So this means that this spring is providing same amount of downward force. This was 60, I think, 60 G. This was providing 45 G, and this was providing 80 G. So if everything else is the same except A, so, and the beam is still in equilibrium, this means that the spring is providing 60 G now. Furthermore, the beam is 0.8 meters above the horizontal ground, but the unstretched length is 0.959 meters. So we can find out the extension. So extension x is equal to 0.8 minus 0.59. That is 0.21. You can calculate this also. 0.21, right? So force is equal to kx. K is equal to F over X. F, we are supplying, it is applying 9.60 times by 9.81, and extension is 0.21 meters. So 60 times by 9.81 divided by 0.21. So we get 2800 roughly. So you could say 2800. So 280, let's say 3 newtons per meter, and you can rewrite it as 2800 newtons per meter. So sorry, 28. Now calculate the elastic potential energy of the spring. So we have spring constant, we have x. So elastic potential energy is equal to half kx squared. So half times by the, you can write that 2800 also. You can use the 60G also using half fx. So either way, it's one and the same thing. Because we also have the f and the extension at the same time. So 2800 times by extension was 0.21 squared, or you can write it as half fx, half times by 60 times by 9.81, that is the force, and the extension is 0.21. And as you can see, they will have very little difference because we are using 2800, not 2803. So 0.5 times by 2800 times by 0.21 squared is 61.74. Let's first write the values and then we'll see how to figure this out. 0.5 times by 60 times by 9.81 times by 0.21. As you can see, 61.8. 61.803. And as you can see, this would have been the answer to two significant figures also. So 62, we can write 62 joules. Okay, moving on. Define power. Power is also an easy definition. It's the work done per unit time. So work done. It is defined, actually, you should write the full sentence. Power is defined as the rate of work done you could also write it as work done per unit time. Okay. An electric car is powered by a motor. The car is traveling at a constant speed of 35 meters per second along a straight horizontal road. There is a total resistive force of 1750 newtons. Okay, so one thing often students forget is it is traveling at a constant speed, so there is no acceleration. So that means that the driving force will also be 1750 and equal to the resistive force. So that's why there is no acceleration. So the work done by the car, by the engine, is going to be work done against the total resistive force. So calculate the power transmitted to the wheels by the car of the motor. So you can just simply say that the work done by car is equal to work done. You can see the instead you can say motor also. Work done against resistive force. Okay. Uh, Similarly, you can convert the same statement into power also. So power expended, power transmitted by the car motor against the resistive force. So when you divide this entire thing by time, this becomes a definition of power. So power is equal to Fv equals to force is 1750 and constant speed is given as 35. 61,000. So we can just simply write it as 61,000 also watts. You can write it in standard form also if you want. Calculate the useful work done by the motor when the car travels a distance of 17 kilometers. So useful work is basically the work output. So this is going to be any definition, force times by displacement. Force is, again, it's since it is working against, since we wrote over here that the work done by motor is same as work done against resistive force. So this is 1750 times by 17 kilometers. So 17,000. So 1750 times by 17,000. So you get 29 million or 2.9 10 raised to power 7. So you can write it as, I think, 3 also. So 2.975 10 7. So 3.0 10 raised to power 7. Okay, right. Okay, the potential difference, P potential difference across the motor has a constant value of 600 volts and the motor has an efficiency of 85%. Calculate the current in the motor. Okay, so we know that the efficiency is equal to useful power output and divided by power input. So if we can find out the power input, useful power output we found out to be this one. No, sorry. Useful work done by the motor. No, sorry. No. This one. 61,000. Because this is the power that is transmitted by the motor. So 61,000 divided by efficiency, we need to write it in the form of decimal, or you can even write 85% also. The calculator will take care of that. 61,000 divided by 0.85. This is, let's first write the actual value, 71764.7 watt. Now we need to convert this into current. First let's write P is equal to IV. Then I will be P over V. Power is 71764.7 divided by voltage. This is 600. So this divided by 600, this is almost 120. So 120. So it would be better if you write the intermediate values also. Okay. The car in B now reaches a slope, as shown in figure 3.2. The car continues down the slope at the same speed as in B. State and explain the effect, if any, of the slope on the air resistance acting on the car and the current in the motor. Now, to understand these 2 points, we need to look at how the slope affects its power generation by the motor. So, first off, the air resistance. We know that the drag or the drag force of the air resistance is proportional to the square of the velocity. When we are familiar with this application in the terminal velocity case also, free fall in the air. So since the velocity is the same, the air resistance remains the same. So since you could say air resistance is affected by or related to speed of the object, since speed remains the same, so does the air resistance. Now, the current in the motor, that is now going to be a different thing. Now, first off, the air resistance is the same. That means we're still getting 1750 newtons this way. However, before we consider the power supplied by or the force provided by the motor to the wheels, we also have to consider the component of the weight that is now acting parallel to the road. Weight acts downwards, but there will be a component parallel to the slope. So basically that will be, let's use a different color to highlight that. So this would be weight sine theta. So the sum of forces, if we write according to the Newton's second law, sum of forces, since the body is going downwards, we'll keep this direction downwards. So force plus W sine theta or mg sine theta, whatever you want to write it as, minus 1750 equals to 0. Previously, it was just F minus 1750. So now, if this is after the slope. So to find out F, this would be 1750 minus W sine theta. This is with slope. If we do without slope, we would have had F equals to 1750. So again, this is with slope. And this one is without slope. So obviously we can see that with the slope, due to the component of weight acting parallel to the inclined plane down the slope, the power generated or the force provided by the motor is now less. So we can say that due to due to the component of weight down the slope, less force is required, and consequently lesser power, sorry, this should be lesser power is produced by the motor. Okay, moving on. State the principle of superposition. Okay, so we have this in the principle of superposition states that when two or more waves meet, the displacement of the resulting wave is the sum of displacement of the individual waves. You could actually, this is actually slightly better. So it states that when two or more waves meet, two or more waves meet at a point, the resultant or resulting displacement is the sum of individual displacements of the waves at that point. That's it. Okay, all right. Light of wavelength 7.2 10 raised to the power minus 7 is incident normally on a double slit. As shown, the screen is at a distance d from the double slit and the screen are parallel. Separation of the slits in the double slit arrangement is 0.16, and the separation this splits, this is actually a, the lambda is equal to ax over d. Basically that's the formula. The resulting interference pattern on the screen contains 9 dark fringes as shown. Okay, so let's see what we actually need. The distance between the centers of the first and the ninth dark fringe is 3.2 centimeters. Okay, calculate d. Okay, so since we have this formula over here, lambda is equal to ax over d. For d, we will need ax over d. X is the fringe spacing. So A was already given to us. A was already given to us 0.16 millimeters. We need to convert this into meters. So 0.16 10 raised to power minus 3. Fringe spacing 3.2 centimeter. So as you can see, fringe 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to divide this not by 9. See, we need this distance. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we need to divide this distance by 8, not 9. So this is a common mistake you can make. So 3.2, 10 raised to power minus 2. divided by 8, and sorry, this was lambda. Lambda was 7.2, 10 raised to power minus 7. Okay, so let's figure this out. So 0.16 times by 3.2 divided by 7.2 divided by 8 times by 10 raised to power minus 3 minus 2 plus 7. We get 0.8. 0.88, sorry, 8 recurring, which is like saying 0. Oh, sorry, no, 0.89, you can say. Okay, moving on. The slit separation is now gradually decreased from 0.16 millimeter to 0.04 millimeter. The distance between the centers of the adjacent dark fringes is x. Figure 4.3, sketch the variation of x with slit separation. Okay, so we need to figure out what's the relationship. So lambda is equal to ax over d. What is changing now? Lambda is constant, d is constant. So lambda d is now constant, which means ax is constant. So you can write it as a is equal to whatever x times by constant, or you can write it as a1 over, that means a inversely proportional to x. Now, how do we how do we sketch this now? So we need a few values, obviously. So at 0.16 millimeters, we had fringe separation. That was, we need to figure out in that. 3.2 divided by 8, 0.4. So at 0. Slit separation was 0.16, we had 0.4. Okay, so this is going to just simply increase. So we can use this thing. We already know the lambda times by d constant. So since this is since x is on y, so we can write it as x is equal to 1 over a, and the constant value is 7.2, 10 raised to power minus 7, and d is 3 point, no, sorry, d was 0.89. Okay, so this is our constant. Okay, this will remain our constant. Or another way you can do that is x1 a1, x2 a2. This one would be more easy because we don't have to change the units anymore. So if we continue using 0.16 and 0.4 centimeter and millimeter, we can continue using the x and a in that form. By the way, 0.16 was a, not x. So, right, okay. Now we want to figure out what's the slit separation at 0.12. So x would be 0.16 times by 0.4 divided by 0.12. So just to show you the process, after that we can just simply plug in the values. Times by 0.1, 4 divided by 0.12. So this is 0.53. So 0.5 is over here, and since 0.4 is represented over 10, which means that each small square represents 0.04. So that is right. So if we divide this further by 0.04, we get 13.3. So that means this is, sorry, my bad. This was 0.6. You were right. This is 10 and then 13. 1, 2, 3. So roughly about this. right? Okay, now for the 0.08, 0.08, that's 0.8. Okay, now 0.04, 1.6, and there it goes. So we already knew what the relationship was because we already found it over here. So x was directly proportional to a. So that's basically what we had over here. So simply we just need to sketch it. That's it. So you can mark for clearly, and that's it. Simply. Okay, moving on. Use the definitions of speed, v, frequency, and wavelength to derive the wave equation. Okay. Okay. So they have phrased this question very differently. So we have to be very careful and do this question according to what the question is asking us. So normally what we would have done is we would have said v is equal to distance or displacement over time. So in one period, we could say that s is equal to lambda because obviously from one full wave from one point to the next point in phase, and time period would be equal to t, and then we would just simply do lambda over t. Finally f would be 1 over t, and that would just go from f lambda. However, they said use the definitions of speed, frequency, and wavelength to derive the equation. So we can't actually use this. So because we haven't actually used the definition of frequency and wavelength properly. So to forget about this, definitions of frequency and wavelength, I'm sure you already know, but just to show you, we have written them also, and you'd be surprised what you would actually need from this. Okay, all right. So distance between wavelength is the distance between two consecutive points on a wave that are in phase. Average time period, total time elapsed over total number of waves, and frequency, number of waves divided by total time elapsed. Similarly, you could also do wavelength, distance divided by oscillations. So we can go over here. So we need a definition. So lambda is equal to distance between two points that are in phase frequency is number of oscillations in 1 second, and v is equal to display rate of change of displacement. Okay, so we can write this in words also. We can do this in sort of like formulae also. Okay, all right. Now we can write the formulas also. So some distance s divided by number of oscillations some distance s. So actually you should write s is equal to displacement of wave. Number of oscillations would be number of oscillations in 1 second. So number of oscillations divided by time, total time basically. We also saw this over here. Sorry, my bad. Number of complete waves, number of oscillations divided by total time elapsed. Okay. Now this is rate of change of displacement, so S over T, or S over time basically. So right, okay. Time T, okay. So now we need a description of S. So using this one first, lambda is equal to S over number of oscillations. I'm just going to write it like this. So therefore, S is lambda times by number of oscillations. Then we have F, which is equal to number of oscillations over time. So therefore, time is number of oscillations over F. And finally, V would be S over T. So as you can see, lambda, sorry, S is lambda times by number of oscillations, divided by time. Time is given as number of oscillations divided by F. So number of oscillations divided by F. So therefore, F lambda V. Because as you can see over here, number of oscillations and number of oscillations will get cancelled. So this is what we're left with. And this is using the definitions of speed, frequency, and wavelength. This is the only way we can do this, according to what they have asked us to do. Okay, all right, moving on. A source of sound waves of frequency 236 Hz is traveling at a constant velocity of 20 meters per second. Stationary observer has a microphone connected to a cathode ray oscilloscope, and the microphone detects the sound waves as the source moves directly towards the observer. So we are expecting a Doppler effect. Okay. The time based on the CRO is set to 1 milliseconds per division. Calculate the frequency of the sound waves detected by the microphone. So first off, we need the time period. So time period T. So time period T. Okay. So we have, if this is one division, we have 1, 2, 3, 4. 4 divisions, right? So time period T would be 4 divisions times by 1 milliseconds per division. So we are left with 4 milliseconds. Frequency is 1 over time. So this would be 4 10 raised to the power minus 3 seconds. So this would become actually 1000 divided by 4. Simply just 1 divided by 4 times. So this is going to be 250. 250. Determine the speed of the sound in the air here. So since it is moving towards the observed frequency would be V over V minus Vs F, where V is the speed of sound in air and Vs is the speed of object or source basically. Source speed was 20. So what is observed is 236. So what is observed? No, sorry, what is observed is 250. My bad. The original was 236. V is what we are looking for. 236. So cross multiplied a little bit. So 250V minus 250 times by 20, that is going to be 5,000, equals to 236V. So therefore 250 minus 236, that is just simply 14. 14V equals to 5,000. So 5,000 divided by 14, that is going to be 357, roughly about 360. Okay, all right, moving on. A nichrome wire of length 45 centimeter and a cross-sectional area is connected to the circuit as shown. The resistance of X is 1.1 ohms. The cell has electromotive force of 1.3 volts and negligible internal resistance. Calculate the current in X. So I is just simply V over R. So V is 1.3 and R is 1.1. So 1.3 divided by 1.1 is just simply 1.18, or just simply 1.2. Okay. The number density of charge carriers, electrons in nichrome, is this. Calculate the average drift speed of the charge carriers in X. So we know that I is equal to NAQV. So drift speed, mean drift speed, I over NAQ, where Q is the fundamental charge. Current is given as 1.2 amps. Number density is given as 8.5, 10 raised to power 28. Do we have the cross-sectional area? Yes, 4.7, 10 raised to power minus 7. And the fundamental charge, 1.6, 10 raised to power minus 90. Okay, so we have 1.2 divided by 8.5 divided by 4.7 divided by 1.6 times by 10 raised to power minus 28 plus 7 plus 19. So we get this value. Let's convert it into standard form. We get 1.877, 10 raised to power minus 4. So this is 1.9, 10 raised to power minus 4. Calculate the resistivity of the nichrome. So resistivity is, we know resistance is resistivity L over A. So resistivity will be R A over L. So resistance we found out to be 1.1 ohms, 4.7, 10 raised to power minus 7. Length, what was the length? 45 centimeter, okay. So 0.45 meters. So 1.1 times by 4.7 divided by 0.45 times by 10 raised to power minus 7. Therefore, this is 1.14, 10 raised to power minus 6. So we can say 1.11, 10 raised to power minus 6 ohm meters. Okay. Wire Y is identical to wire X. Wire Y is added to the circuit in parallel with wire X. Okay, so basically it's just like two resistors in parallel and two identical resistors. State and explain the effect, if any, of this change on the reading of the ammeter. Since the net resistance So for example, if we have two identical resistors in uh, in parallel, this is R, the net resistance or the effective resistance would be half of that. So if resistance is half, the current would be doubled. So that's what we will write. So net resistance is halved. So current will be current or the reading on the ammeter will double as the potential difference is the same. Okay. The average drift speed of the charge carriers X. Now, the one thing to notice over here, we said current will double. So previously, if this was I, now both of these will have I. So the current is now registering to be 2I. So since the current is the same, we have V over I and A Q. Everything else is same. I is same, N is same, A is same, Q is same. So since current flowing through X remains the same, the average drift speed will also remain the same. That's it. Simple. Okay. Moving on. Nitrogen is an unstable isotope of nitrogen that decays by emission of radiation to carbon 12(6). Okay. Complete the full nuclear equation for decay, including all the particles involved. Okay, so first off, we need to, write this C12 and 6. Now, to see what is happening over here, the proton number is decreasing by 1. So that means one proton is decaying. So proton is decaying into a neutron. And now here is the thing. This is the beta plus decay. So this means that there is going to be a beta plus charge, beta plus particle and an electron neutrino in this. So we need all the particles involved. So we have beta plus charge, which has 0 mass, but 1 charge. Whether you write plus or not, it doesn't matter. Only if it was negative, then we would write minus. Then you have neutrino, B, electron neutrino, 0, 0. That's it. Hydrogen 1 is an isotope of hydrogen. An atom of hydrogen 1 comprises a proton with an orbiting electron. An antiparticle equivalent of hydrogen 1 comprises an antiproton with an orbiting positron. Okay, the antiquarks in the antiproton are the antiparticles of the quarks in a proton. State the charge on the positron in terms of the elementary charge. So if electron has a negative 1e charge, it has positive 1e charge. State the group class of fundamental particle to which the positron belongs. This is easy. They are leptons, electrons, and positrons. They belong to the lepton class. Okay. In table 7.1, state the flavor and charge of the three antiquarks that comprise the antiproton. So proton has up, up, down. Up, both ups have 2/3 E, 2/3 E, and down has minus 1/3 E. Since we have uh, opposite, anti, so we have anti-up, anti-up, anti-down. So we will have minus 2/3 E, minus 2/3 E, and plus 1/3 E. So the bar over this indicates the anti-quark. That's it. All right, and that was the end of this paper. Now, if you feel that I made a mistake somewhere, if you feel that I wasn't able to explain a certain part properly, do reach out in the comments. I will try to explain it again. And yeah, so as you have seen that we have used these grade booster products. So do check this out on Patreon. We will give out the link in the description. Meanwhile, take care and we'll see each other in the next video. Bye-bye.